Solar panels work by converting sunlight into electricity through a process called the photovoltaic effect. Here's a detailed breakdown of how this process works. 1. Photovoltaic PV cells. The basics. Structure. A solar panel is composed of many photovoltaic PV cells. Each PV cell is usually made of silicon, a semiconductor material. PV cells are the essential building blocks that convert sunlight into electrical energy. Types of PV cells. Monocrystalline silicon, made from a single crystal of silicon, offering high efficiency. Polycrystalline silicon, made from multiple silicon crystals, with slightly lower efficiency but cheaper to produce. Thin film solar cells, made from materials like cadmium telluride or amorphous silicon, these are flexible but less efficient. 2. The photovoltaic effect, how energy conversion happens. Light absorption. When sunlight composed of photons strikes a solar panel, the photons hit the silicon cells. This light energy knocks electrons loose from the atoms in the silicon. Creation of electron-hole pairs. In silicon, light energy excites electrons, creating free electrons and holes positively charged gaps left behind. Electric field formation. Each PV cell has 2 layers. N-type silicon. This has an excess of electrons. P-type silicon. This has an excess of holes or a shortage of electrons. When these layers are brought together, they form a p-n junction. The electric field at the junction helps push the freed electrons towards the N-type side and the holes toward the P-type side. 3. Generating an electric current. Movement of electrons. The electric field at the p-n junction forces the separated electrons to move towards the N-type layer. Simultaneously, the holes move towards the P-type layer. Current flow. The movement of these electrons generates a direct current DC. When the PV cells are connected to an external circuit, the electrons flow through it, creating an electric current that can be used to power devices. 4. Solar panel components. Encapsulation. PV cells are encapsulated between layers of protective materials, typically glass on the top and a polymer back sheet. This protects the cells from weather conditions. Frame. The entire assembly is held together with an aluminum frame, which provides rigidity and allows for easy mounting. Junction box. The junction box is connected to the back of the solar panel and contains diodes to prevent reverse current flow. It is where the positive and negative terminals of the solar panel connect. 5. From DC to AC, the role of the inverter. Most home appliances and the grid operate on alternating current, AC, rather than direct current, DC. Therefore, an inverter is needed to convert the DC generated by the solar panels into AC. Types of inverters. String inverters, used for multiple panels connected in series. Microinverters, installed at the individual panel level, allowing for better efficiency if panels are shaded or oriented differently. Power optimizers, used in combination with string inverters, they adjust the output of individual panels to maximize efficiency. 6. Energy storage and usage. Direct use. During the day, the electricity generated can be directly used to power appliances or sold back to the grid. Energy storage. Excess energy can be stored in batteries for use during periods without sunlight, such as at night or on cloudy days. Lithium-ion batteries are commonly used for their efficiency and lifespan. Grid-tied systems. These systems feed excess electricity back into the power grid. Many countries have net metering policies, allowing homeowners to receive credit for the electricity they export. Off-grid systems. These are completely independent of the power grid and rely on batteries to store electricity for nighttime or cloudy periods. 7. Efficiency factors. Angle and orientation. The efficiency of solar panels depends on their orientation and tilt relative to the sun. Solar tracking systems adjust the angle of panels throughout the day to maximize sunlight exposure. Temperature. High temperatures can reduce the efficiency of PV cells, even though they need sunlight to produce electricity. Shading. Shading from trees, buildings, or other obstructions can reduce the amount of light hitting the panels, decreasing energy production. 8. Output and power rating. Wattage. Solar panels are rated in watts W, indicating the power output under standard conditions, usually 1000 watts per square meter of sunlight. For example, a 300-watt panel produces 300 watts of power per hour under ideal conditions. Performance ratio PR. This ratio accounts for losses in the system, like conversion losses in the inverter and temperature effects. It gives a better estimate of the real-world output of a solar installation. Kilowatt-hours kWh. The energy output over time is measured in kilowatt-hours, which indicates how much energy a panel can produce per day or per year. Summary. Solar panels use silicon-based photovoltaic cells to convert sunlight into direct current DC electricity through the photovoltaic effect. An inverter converts this DC into alternating current AC, which can be used to power homes or fed back into the grid. Various factors like temperature, shading, and orientation affect the efficiency of solar panels. With advancements in materials and energy storage systems, solar panels are becoming a key part of renewable energy solutions.